Okay, today's topic is a little different from rotational solids. It's called cross-sectional solids. And what it's about is, instead of rotating figures around, we're going to still slice them up. They're going to be formed with a base. And what I'm looking at here is the x and y axis sort of flattened out. And they have a base. The base is formed by two curves. And for the most part, a side of a cross-section, what we'll do is we're going to build the cross-section up. A slice of the cross-section will come out of here. And depending on the direction it's cutting, it'll be dy or dx. In this case, it'll be dx. And we're going to look at how long this piece is right here. Now, the nice part about cross-sectional solids is that we've made them of two curves. And they are always, we call it S for side, usually, or for base. That distance S will always be equal to upper minus lower. And what happens is you'll have a base, and then what you'll be told is that the shape of the cross-section, meaning if we sliced it out of there, it's going to form some sort of shape. Sometimes it's a square, sometimes it's a triangle, sometimes it's a half circle, and depending on what it is, we get different things. But as an example, if I took a slice out of here, and that length was S, the cross-section would look like a solid whose face is a square. Let's face square. If you came over to here and we took a cross-sectional piece, its face, however long this is S, would form a square. And once again over here, the face would form a square. So it would have almost like little pats of butter, but the wider the area, the wider the piece of butter, and the side of the piece of butter would always be formed by the equation upper minus lower. Now, before we talk about how to solve these problems, let's just quickly take a look at some general solids. And these are things that we could find the volume for. Well, the volume always has a height, right? A height. And the volume of something is always equal to the face of it, the top part, times its height. So if this is a circle, it's pi r squared. And the volume of this thing is pi r squared h. If this one is S, side is S, and the face of the area is S squared, so the volume is S squared h. If this is 1/2 base times height, we'll use a different letter for height, we use E. It's 1/2 base times height times the whole thing. And for an irregular shape, if I just can find the area of the face, well, the volume of the whole thing is the face times the height. So we're going to look at one generic problem now. Let's come back over to here, where I'm going to slice up something, and its faces are going to be squares. And we know with a square, if the face is a square, if I know the base is S, I know this side is S, I know the area of the face is S squared, and it's going to be equal to S squared H. And depending on how I slice it horizontally or vertically, we almost always slice these horizontally. It's probably going to be S squared dx. That will be one slice, so the integral of the whole thing is going to give me the volume of the entire figure. And for the most part, it's always going to be, no matter the shape, you're going to be doing S squared dx, maybe with some constant out in front, and S is always going to be upper minus lower. So let's try an example of a problem and see what we come up with. I've flattened this thing out so you can see the x-axis down low and the y-axis up top. I've got a base that is formed by the boundaries of the curve y equals x and y equals x squared. Okay, so back to the problem at hand. The base is formed by there, and the cross-sections are squares. Okay, so thinking about it this way, the base of this is forming the base of the problem. So I'm going to look at one slice. Oh, let me draw the slice better. The face forms a square. A slice, I know, terrible slice, looks kind of like that. Well, the width of each slice is going along the x-axis, so it's going to be dx. And the side, the s, is going to be the upper curve, which is y equals x, minus the lower curve, which is y equals x squared. And it's going to start at 0, and it's going to go to 1. And what's going to happen is it's going to keep slicing this up. It's going to find all the individual slices, the big pats of butter and the small pats of butter. It's going to add them all together. So what I'm going to do is flip to a new page here. Another page. So for this problem, I'm doing the integral from 0 to 1 of s squared dx. I know that s is going to be equal to upper minus lower squared dx, much like in the other problems that we worked on. Okay, so it's going to be the integral from 0 to 1 of the upper curve, which was y equals x, or y1 minus y2 squared dx, upper minus lower. I'm going to get everything in terms of x, so let's do the integral from 0 to 1 of x minus x squared dx, and that's how you set pretty much all of them up. Squared dx. I don't have to, but I'm going to solve this one out algebraically because I think I can do it. So you're going to go from 0 to 1, this is something squared. I'm going to use that same rule I did from before. Square the first term, square the last term, add 2 times the 2 terms together. So it's going to be this first term squared, the last term squared, so the fourth, and x times negative x squared is negative x cubed, so that's going to be negative 2x cubed dx. So now that I set that up, I can integrate it. So I'm going to go ahead and integrate. Notice there's no pi in here. When you have squares and triangles, there's no pi's. So I'm going to set this one up. It's going to be x to the third over 3 minus x to the fourth over 2/4 plus, we'll put plus there, minus x to the fifth over 5 from 0 to 1. We're very happy with those limits of integration because they're easy ones to work with. Let me flip to the next page here and I'll rewrite this down. So I'm going to fill the numbers on in now. So it's going to be, once again, let me write it down, minus x to the fourth over 2, because it was 2/4, I simplified it. 5 between 0 and 1. So if we substitute those in, we get 1/2 minus 1/2 plus 1/5. And so the minus 0 minus 0 plus 0. Right, thought so, that should have been plus. My bad. Because negative x squared is positive x to the fourth. Thought so. Equals, cancel, cancel. The answer is 1/5. There's a whole bunch of various shapes. In the next video, I'm going to show you where the formula comes from. But in the end, every problem is s squared dx with some sort of constant out front. We'll discuss what those constants are.